Okay, and here we go. Back with question number 32. All right, so it says the diagram below shows a simple circuit. It's got a battery, a light bulb, and a switch. The energy transformation that occurs in the circuit above when the switch is closed is, and the correct answer is chemical energy to electrical energy to light and thermal energy. So our battery is the source of the power, and batteries store chemical energy. When the switch is closed, electrons that have that potential energy are allowed to flow. So now we have movement of electrons. So then we get electrical energy, and that electrical energy lights up our light bulb and also produces some excess heat. So there we have it. Okay, next question. When a switch, a variable resistor, a light bulb, and a motor are connected in a circuit such as the one shown below, the circuit will operate as follows. The switch will control both the motor and the light bulb. So if they say it's going to control both the motor and the light bulb, it means it's going to be able to turn on or off both the light and the motor at the same time. Okay, so if we open the switch, the circuit's going to go off and both motor and light bulb will shut off. And when we close it, both the motor and the light will turn on. And then it says the user will be able to control the brightness of the light bulb. So that's going to be because of the variable resistor. So we did talk about this briefly, but if we have a resistor, basically slows down the flow of electrons. So we've got a light bulb. If we had a light bulb connected to a battery, that's not connected to a battery. If there was no resistor here, was connected straight through with a wire, we would have a better flow of electrons. But when we put the resistor in there, it slows that flow of electrons and that causes the light to be dimmer. So a variable resistor, which would look something like this, means that we can change the resistance. We can have more resistance or less resistance, and that makes the light bulb get brighter or dimmer. Okay, so in order for that change to happen, that variable resistor would have to be in series with the light bulb because it's slowing down that flow to the light bulb. All right, so that could be one hint. We know we have to have a series connection with the variable resistor and the light bulb. So I'm going to have my light bulb in one of these two spots and my variable resistor in one of these two spots. So I'm going to look down below for Y and Z and look at which ones have that variable resistor and light bulb. And there's actually only one combination here that included both of those. But let's just see then, according to this answer, it says the switch would be at W. So this would be my switch. And then my motor would have to be here. So motor, light, variable resistor, switch. So let's see, if I open this circuit, so in order to have electricity flow, we have to have a completely closed circuit. So it has to be able to go here through the motor and continue back to the battery and to keep the electricity flowing. But electricity cannot get through when the switch is open, so the motor would not operate. Now, same thing goes for the light. If our electricity has to flow through a resistor, through the light, it has to make a return path all the way to the battery. But if the switch is open, it would not flow. So in this case, the switch is definitely going to shut both of those off at the same time. And of course, if we were to close the switch and then connect that, so now we have a connection, then electricity would flow through the motor and back to the battery. It would flow through the light and back to the battery again. So it would also then turn it on. So that's working the way it's supposed to. The switch is controlling both the motor and the light at the same time. And then we already set this up so that our variable resistor was in series with our light, so that we could turn the dimming effect on. We could dim the light or turn it up so it gets more bright. And then that completes that question. Okay, next one. Jake needs to repair a car's stereo system. The system contains a stereo and a fuse that are connected in series and two speakers that are connected in parallel. So let's pick this apart. Stereo and fuse in series. Let's look for a stereo and fuse in series. Here's a fuse and stereo, but those are in parallel. Here's a stereo and fuse in series, so that looks good. And then two speakers in parallel. There we have it. Two speakers in parallel. So that's answer is B. Next one, a grade 9 student used the ammeter to measure the current of a circuit consisting of a bulb, an ammeter, and a 1.5 volt battery. She then changed the voltage using various batteries and measured the resulting currents using the same bulb and ammeter. So she used the same bulb, the same ammeter. The only thing she changed was the battery. First, she had a 1.5 volt and measured 0.7 amps or milliamps of current. And then she put a 3 volt battery and measured 1.5 milliamps, and so on. And if we pay attention, we can see that each time she's replacing it with a battery that is 1.5 volts more than what it was previously. So each time we're changing by the same amount, right? By 1.5, by 1.5 more, plus 1.5 again, and so on. And each time here, we are changing by about how much? Here's 0.8, and then 0.7, and then 0.7, and then 0.8, and then 0.7. So if we average that out, it's going to be pretty close to 0.7. So we can see that's changing pretty consistently as well. So now the question asks, based on the information in the graph, if a 10.5 volt battery were used, then the expected ammeter reading would be. So once again, from 9 to 10.5, we've changed by the same amount as we've seen so far. So I would predict that this would also increase once again by 0.7 milliamps. So if our last one was 4.4 plus 0.7, we're going to get 5.1 milliamps, and that gives us our answer B. They also put a graph here. You know, we could use the graph to try and predict. This would be 11 here. 10.5 would be somewhere there, right? If we extrapolated this linear line here, we would look over here, and it looks just a little bit above 5. So I could use my graph to figure that out as well. But either way, in this case, we didn't even actually need the graph, although it did help point out to us that this is a linear equation, right? So, okay, next question. Question 36. A student is testing the conductivity of 4 different substances. He uses 2.5 volt battery and records the current in the circuit of each of the 4 substances. The chart below indicates the current measured. Okay, so he's hooked it up to some kind of circuit. Maybe there's a light bulb, who knows? But he's measuring the current. The only thing he's changing is the different material, the conductor. So, okay, so he's measuring the current flowing through these different substances, and we have 2.5 amps being the highest, 2.4 amps being the next one, and 37 milliamps. Remember, milliamps is going to be like 0.037 amps. So think about it. We have our 10th place, our 100th place, our 1000th place. So milli means 1,000th. So 37 1,000th of an amp. So that's quite small. And then 0.01 milliamps would be even smaller than that. So there's practically no current flowing here at all. It says, which one is most likely an insulator? Well, good conductors allow current to flow, like these two. This one seems to be a poor conductor, but it still does conduct electricity. However, this one is practically not conducting any electricity at all. So we would say substance R is likely an insulator. Ratings for an electrical device says that the voltage is 100, current is 4 amps, resistance is 25 ohms. What's the power? So our power formula is current times voltage. And we just simply multiply 4 amps times 100 volts gives us 400 watts of power. Okay, so that's D. Energy measurement for different systems. System P, System Q, and System R. System P has an energy input of 500 joules and gets 260 joules of useful output energy. Q has 90 in and gets 30 out. And J has 15 in and gets 12 out. So remember, our efficiency is determined by our output over our input. So when we test all of these, we're going to get different percentages. Here I would take 260 and divide by 520. Without calculating that, I can say it's a little bit over half. So it'd be a little bit bigger than 50%. It's in and around that area. This is a little bit bigger than 1/3. You can use your calculator to verify all this. I'm just trying to be quicker. This would be a little bigger than 30%. And 12 out of 15, if we divide that, we actually get exactly 0.8, which is exactly 80%. So that's definitely the highest one. You could calculate these with your calculator to get a more exact answer, but I'm just not going to do that right now. I know that this one is definitely the highest, so that's the one we're going to use. Okay. Next question. Which of the following actions will not reduce waste of energy in a home? So A, replacing single pane windows with double pane windows. Air is a good insulator. So if I have, here's a wall of my home, and here's the cold outside air. That's a snowflake. A single pane of glass is not a good insulator. It's going to allow a lot of heat to escape from the home through the glass. Okay, but if we put in a piece of double paned glass, we now have this air gap, and air is a pretty good insulator. So we're going to have less heat escape, maybe a little bit, but not nearly as much. So that would actually help improve reduce energy waste. Okay, so that's not one that will not reduce it. Installing a programmable thermostat. So if we just set a temperature for our home and we just leave it at that all day, even when we leave the house, we're burning a lot of fuel to try and heat our home when we're not there. So a programmable thermostat can allow those temperatures to be a little bit cooler when we're not at home, and the furnace will shut off and save energy. So programmable thermostats save energy. Wrapping and insulating a blanket around the hot water tank. If we have hot water tanks work by burning some fuel and heating up water that's inside of it. Okay, but some of that heat is going to escape. And then we're going to have to, the hot water turns on again, the flame turns on again, keeps heating that hot water. But if we put a insulating blanket on top, a lot less of that heat is going to escape, and then the flames will not need to turn on, and we will save energy. So that's another way to save energy. Installing an air conditioner to reduce temperatures. Well, air conditioners use energy to make the home cooler. So that's definitely not an energy saving device, right? If anything, it's going to use more energy. So this is not a way to reduce energy waste. So that's the answer we're looking for there. Question number 39. Which of the following two methods of power generation provide the least consistent energy? So we're talking options are wind, solar, hydro, and nuclear. So wind energy depends on the wind blowing. That's not happening all the time, so that would be one of the less reliable ones. That's a big fan, supposedly. Okay, and solar power. Very good when the sun is shining. Okay, but not so good when the sun is not shining. So that's also not a very reliable source of energy. So that's why answer is A. Hydro, as we discussed, is, for example, you might have a water here. There's a dam, and excuse me, we let that water flow through. Now, water and rivers, as long as we have healthy water systems, that water is always going to be present there and flowing. So hydro is quite reliable. And then nuclear, again, those reactions take place for very long periods of time. So nuclear power would also be considered a reliable source of energy compared to those. So wind and solar power definitely the least reliable, or least consistent. Okay, advantages and disadvantages of a particular energy source are given in the following table. Advantages: cost effective, readily available, so easy to obtain, reliable source of energy, so works very well. Disadvantages: non-renewable resource, contributes to global warming, disrupts natural habitats. The energy source being described in the table above is most likely solar. No, because that's a renewable resource. Biomass, that's a renewable. Geothermal is also a renewable resource, whereas natural gas is a non-renewable resource. It is readily available, cost effective, and reliable, but it does contribute to global warming, disrupts natural habitats because they have to set up sites to excavate and obtain the natural gas from below the earth. And of course, it's a non-renewable. When it's burnt up and gone, it's burnt up and gone. All right, last leg of this PAT. Here we go. The first four planets from the sun are called the inner planets. The four planets that are furthest from the sun are called the outer planets. Which of the tables below lists some of the key characteristics that distinguish outer planets from inner planets in our solar system? So our inner planets, remember, our outer planets are large and gaseous, like Jupiter. Our inner planets are smaller and terrestrial, meaning that they are like rock-like. Okay, so inner planets are not gaseous. Inner planets are not gaseous. We can get rid of those two options right away. Inner planets are terrestrial. Outer planets are gaseous. Yes, inner planets are not large. They're smaller. The outer planets are the large ones. So inner planets are terrestrial and small, and they have few natural satellites. Outer planets are gaseous, large, and many natural satellites. So remember, satellite just means anything that orbits something else. Artificial satellites are the ones that are created by man, and they orbit the Earth, for example. And natural satellites would be like Jupiter has many moons around it. Okay. Which primary property of a star does the above spectral analysis determine? So we didn't talk about this a lot in class. We may have kind of briefly read it in the book, but we didn't have any real questions about this one that we answered. So we'll just talk about this now. So spectral analysis, this is a way of determining the composition of things. So we have a star far away here in the galaxy, and it's emitting light waves that travel and make it all the way to us here on Earth. and we can focus devices on that light, and we get that light. Now that light comes, so we've got something called a spectrometer. So when light comes into a spectrometer, uh, it reflects and then refracts this light, and it spreads it out. If you've ever seen like a prism, um, and then a prism splits things and gives those rainbow colors. Now these dark bands here, these show us basically there. So we see all the colors possible when we refract white light into its different wavelengths, and then we get like a rainbow of colors. But then there'll be some bands that are missing. So there's certain elements have been determined to um, use a certain wavelength of energy, and because it uses that wavelength of energy, it emits everything except for certain wavelengths, and that corresponds to particular atoms. So through laboratory testing, they can take an atom and essentially get a fingerprint what sort of light waves it would emit when it's heated. So they can tell based on these patterns, it's like a barcode, what kind of elements are in this sun, in this star. So yeah. Um, so just remember spectral analysis or anything with spectrometer, that's trying to determine the composition. By that we mean like what kind of atoms, what kind of elements is that star made of? Okay, so Sally is facing south on March 21st and is trying to find the coordinates of the sun as it sets. So here she is. You can see she's facing this way to the south, and here is the sun over here. Which of the following coordinates most likely describe the location of the sun? So that location we're going to describe by two types of things, altitude and azimuth. So azimuth is the degrees measured from north, starting at 0 degrees and in a clockwise direction. Okay, so when we get to east, that's 90 degrees. When we get to south, that's another 90 degrees, which is 180. When we get over to the west, that's another 90 degrees, which is 270 degrees. And anything in between. So if it's directly to the west, her azimuth is going to be 270 degrees. There were two options that had an azimuth of 270 degrees. Then her altitude is going to be the angle from the horizon to this object. So we can see that this object is low in the sky, so that would be a very small angle. So something like 5 degrees would make sense. Our other option was 85 degrees. If 90 is straight up, 85 degrees would be somewhere right here, right? From the ground up, that would be 85 degrees to get up to here. But our sun is not here, it's down here. Okay, so that's a small angle, 5 degrees. Okay, so here we go. Altitude 5 and azimuth 270. All right, which of the following factors is the main reason an astronaut's muscle mass and bone density decrease while in space? So and we did talk about this, I recall, when we're standing on the Earth, we have gravity pushing down on us. So just the simple fact of standing and moving around, our body has to resist the force of gravity. So that creates kind of a pressure on our body, on our bones, and that helps keep our bones dense. So think about that gravity is pushing down on us in a way, actually more so pulling us into the earth. And we have to resist that force so that we don't collapse into a pile of like a muddy puddle, right? So that sort of pressure is compacting our bones and keeping our bones strong and healthy. When they're in space, they are floating around. That's an astronaut floating around. Okay, and they don't have that force of gravity on them. So the answer to this one is astronauts do not need to support their body weight. Now, it's kind of the way it's worded is maybe a little confusing. So when it says that do not need to support their body weight, they meant like um, they're not forced to have to support their body weight the way we do on Earth. We have to. There's no choice. But here, they don't. Not only do they not need to, they can't. There's no way. They're just floating in space. So it's that idea that they're not having to support their body weight, that they don't get that pressure that keeps our bones compacted. So over time, that can cause problems with the bones. So that's why they do exercise in space to help combat that. But yes, so that would be the correct answer for that one. Okay, so use the following information. Here we have some parts of a astronaut spacesuit: visor. It says liquid cooling and ventilation garment. His visor, his life support system, and extravehicular maneuvering unit. Not quite sure what that looks like. This is kind of a weird looking. Looks like a piece of intestine or something. But what's important are the words extravehicular maneuvering unit. Means it's something he's going to use to move around. Okay, so it says match the space conditions given below with the numbered space suit component above that protect the astronaut while in space. So ultraviolet radiation. So he needs to protect his eyes from ultraviolet radiation. So it's his helmet. Zero gravity. So he's out in space in zero gravity. He's just floating around. So he's going to need something to help him maneuver. So that would be the EMU. Whatever it does, it helps him to maneuver around in space. Extreme temperatures. Well, that's liquid cooling and ventilation. So you can get very hot or very cold in space, depending if he's in the sun or not. So he has a liquid cooling and ventilation garment. And no atmosphere. Without atmosphere, there's no oxygen. You cannot breathe. So his life support system, number 3. That pack has oxygen in it, oxygen supply, among some other things. Okay, so that's that. Number 45. Which of the following statements best compares telescopes based in space to telescopes based on Earth? So let's look at them one by one. Space-based telescopes are generally larger. This is not correct because it takes a lot of investment and effort to get those up into space. They have to be able to be sent up to space in a rocket and then assembled out in space. So yeah, it's setting up very, very large telescopes is not very practical. C, Earth-based telescopes in general cost more to build. That's not correct because, again, it's the whole idea of getting things out into space, which is a great effort and therefore costs a lot of money, a lot of extra money. And Earth-based telescopes explore further into deep space. Again, incorrect. Without restrictions of our atmosphere and having telescopes out in the space, they are able to explore deep into space. That's why we want to have space-based telescopes. The correct answer, though, is space-based telescopes capture. Which of the following statements best compares these? Space-based telescopes capture clearer images. Okay, and that is true. Okay, next question, 46. We've got a chart here. It says radio telescopes receive radio waves from distant planets. So distance from the sun, 1 astronomical unit is the same as 150 million kilometers. So that's exactly how we define an 1 AU, 1 astronautical unit. The definition of that is precisely the distance from the sun to the earth. Okay, so that's 1 astronomical unit away, and the time required for radio waves to travel from the sun are 8.3 minutes to the earth. And Mars is at 1.5 astronomical units away. So if here's our sun, Mars would be further away at 1.5 astronomical units. And they want to know how far or how long would it take required radio waves to travel to the sun. Well, this is just like our math problems, like our scale factor problems. So think about this. If we had the scale factor of these distances, 1.5 to 1, Mars is 1.5 times further away, right? 1.5 astronomical units over 1 astronomical unit. That would be like a scale factor of 1.5. So we're just going to multiply the time. If it's about 1.5 times further away, then it is, or it's, sorry, I should say it's 1.5 times the distance from the sun to the earth. Then the time it takes for the radio waves travel will also be 1.5 times the time. Okay, because they travel at the same speed. So we have to multiply the time from that they take to get to the Earth by this 1.5 factor. So 8.3 times 1.5, and you will get 12.5 minutes. Okay, question 47. Which of the following measurements could be calculated using the process of triangulation? So triangulation is something that can give us the distance between two celestial bodies. So for example, if we want to know the distance from, say, the sun to some distant star, we can, well, here we are on Earth, traveling around, and at one point in the year we're at this extremity, and one point in the year we're at this extremity, and we know our distance to the sun from here and here. So we know this distance between these 2 points, and we can measure towards this object, we can measure an angle. Okay, and so when we know these angles and we know our distance, we can calculate this length here. Okay, so we can use trigonometry and math to calculate this distance. So we can therefore calculate distance from, for example, from our sun to this planet or to this far off object, whatever it might be. Okay, so just remember when you think of triangulation or the word parallax, because that's parallax is what is the phenomenon, I guess, that's associated with triangulation. So either of those two words, that's going to be your key to tell you that we're talking about measuring distance using triangles. Okay. Constellations consist of patterns of stars in the sky. The constellations we recognize today were identified by many ancient civilizations. Which of the following statements best explains why planets are never featured in constellations? So if we see a constellation in the sky, like the Big Dipper, these are stars. And every time we look at the Big Dipper, they always looks that same shape, right? So we can kind of in our minds imagine lines connecting them. So we're saying all of these are stars in this constellation. None of them are planets, and they're asking why. So is it because planets look bigger than stars? Is it because planets are more difficult to see than stars? We can see planets in the night sky with the naked eye, and with telescopes we can get very good pictures of them. Is it because planets have chemical composition different from that of stars? We can still see them. They still look like a point of light in the sky, so that one's definitely a no. Or is it because planets do not maintain fixed position relative to other stars? Now, this is the correct answer. Now, to understand this, think about here we have the sun, and we have some planets rotating around the sun. Okay, and I'm just skipping some of the planets because I don't have room. Let's just assume that this is Earth. Here we are, and we look up into the night sky and we see these planets. Now, these planets are moving around the sun like this, and we can see them move, and they are have different positions in the sky. Now, this might look like a big distance when we think about our solar system and our planets moving around, but when we look at the reality of things, here's our little solar system, and the stars we're looking at are so far away, um, that we don't see any kind of movement. These stars are just out there in a fixed position for us. Whereas these planets are zipping around in our night sky. So while these constellations stay in the same spot, these stars stay in the same spot for us. We have these planets orbiting around our sun. And because they orbit around the sun, they move through our night sky. And they're always changing positions. Whereas the stars out in the planet, these would be, well, the centers of their own solar systems. They might have planets orbiting them, but they are not orbiting around. And on top of that, they're so far away, any movement, we just wouldn't even really see that. But the planets are close to us in comparison. And so we see them zipping by through the night sky. So they're never going to be in the same position. So the answer is planets do not maintain fixed positions relative. Sorry, planets do not maintain fixed positions relative to other planets or stars. They're always kind of moving around. Okay. So, second last question. A geosynchronous orbit occurs when an object orbits Earth at the same rotational rate as the Earth. So think about it. So think about this. So here's the Earth, and it rotates around at a certain speed, at a certain velocity, right? Okay, this is the Earth. There we go. America. So there we go. North Pole. You got the idea. There's Earth. It's spinning around. So pretend we're looking here down at it from the, I don't know, from the top pole. We're just looking at it spinning from above. So if we have something that's in geosynchronous orbit with the Earth, we send this satellite out into space, and it's also rotating at the same number of rotations per amount of time. And so as we turn, if I'm standing here and then the Earth turns, it's later in the day now, I'm standing here, this satellite has also traveled that same number of degrees, and it's going to always be above me. So when the Earth rotates and now I'm standing here, this is also rotating such that it's in a fixed position relative to where I am. Okay, so that's what they're talking about with geosynchronous orbit. So that's why the answer is that it sends signals continuously to a specified area on Earth. It can always be, it's in geosynchronous orbit, it can always be sending signals to this part of the Earth. Why are the other ones wrong? So capture information, about global weather patterns. Well, to do that, it would need to see uh, all parts of the Earth. So it would be better that it's rotating at a different speed, either faster or slower, so that it's getting a look at different parts of the Earth. But it's always, and if it's in sync, it's only looking at one side of the Earth, let's say. Okay, so that's no good. Capture images of the planet from many perspectives. Well, we just said that it can't do that because it's actually in the same position with respect to the Earth. And then D, send messages to multiple receivers anywhere on Earth. So if you notice what they all have in common, they're saying that they can see different parts of the Earth, where as the truth is they can only send signals continuously to a specified area on Earth. Okay, and there's reasons they would want to do that. Maybe they have a satellite that they want to set up in the Earth's orbit to observe a particular part of the Earth. Okay. Last question. A long stay Mars mission with astronauts has been calculated to last approximately 905 Earth days. NASA has broken down the duration of the mission as follows: travel time to Mars, time on Mars' surface, travel time to Earth, and then the total mission time. Research into which of the following areas would be least helpful to support astronauts during a successful long-stay mission, Mars mission. So it doesn't mean they're not helpful at all, but which would be the least helpful. They need spacesuits to survive. There's no water on Earth, so water reclamation is a way that they can essentially create water from other components of the atmosphere, right? Other elements, combine hydrogen and oxygen to make water. And growing food in space, of course, right? That's a long mission. So it'd be difficult to maybe bring all the supplies they need. So they need to find a way to set up, indoor grow labs where they could grow food and cultivate food on Mars. So that's going to be another difficult challenge. Telescopes, compared to those things, really not that helpful. I mean, it's something they might want to do long time in the future, to have maybe telescopes set out there to observe other parts of the universe. I don't know, but it's more important their actual survival on that planet, and all those other things are going to be helpful for that. So the telescopes, in comparison, the least helpful to support them on a mission like that. Okay, and we made it through a full PAT with explanations included. So I hope this helps you. Good luck on your PAT this coming Tuesday. If you have any questions from the other practice PATs, I can go and answer those maybe on a one-by-one basis. You do have the answer keys. So if you're not certain as to why a question is what it is, then please let me know, and I will see if I can go over those or post some solutions or some explanations for you to those. If I have the opportunity, I will post more of these explanation videos on the other PATs, but hopefully this helped. Let me know how's it going. Thank you. Bye.